Okay, good morning. Thanks again to the organizers. It's been a very interesting experience for me. Today I'm going to continue with nuclear reactions in the early universe. In yesterday's, so this is the course organization. You'll recall that we've prescribed exercises for the afternoon session, and we're doing the same thing today. So you should have received a six-page handout for the workshop session this afternoon, which I think is considerably more involved than what we did yesterday. You'll take a running version of the serial code and you'll parallelize it. And so you'll have to get into some aspects of the MPI message passing library, which hopefully is familiar to you. If not, of course, Evan and I will be here to answer your questions. So please avail yourself of Evan's talents. Okay, so today I'm basically going to focus on how we get a unitary reaction network from data. And this is an important feature of quantum mechanics. It corresponds to conservation of probability, and it's currently not being implemented completely or consistently throughout the reaction networks. I put up neutrino energy transport. Possibly we'll have time to get there. I doubt it, because we're going to hear a very interesting 20-minute presentation from Evan on observations of light nuclides, the primordial component of them. And I think that's useful for us to know, for all of us to know, especially theorists, how these abundances are extracted from from astronomical observation. Okay, let me just give you an overview very quickly of the light nuclear reaction program at the lab. Basically consists of two components, the ab initio component and the phenomenological component. I'll talk mainly about the phenomenological component today, but that's just because that's most directly related in terms of the amount of data that you can analyze for astrophysical applications. But the ab initio program is very strong. It's continuing, and we're really starting to get that off the ground. So I don't want you to think that we don't do any basic theory. The motivation, of course, is you take data sets, observations such as integrated cross sections, differential cross sections for unpolarized data, polarization coefficients like asymmetries or spin correlation coefficients. And what you want to do with that data is turn it into a T matrix. And that'll give you information about the resonance spectrum of the nuclides. It's essential, as I've mentioned, and I'll say many times throughout the talk, that one do this parameterization unitarily. And later on in the talk, I'll show you how you can go down the wrong path if you don't enforce unitarity. So the phenomenology program that we have ongoing for 4 or 5 decades now in the group that I work in at Los Alamos uses the R matrix approach, first written down by people the likes of Bohr and Lane and Thomas and Beta and folks like that. I just want to let you know that this also is a very active and ongoing research program. For example, we're putting in, for the first time, 3-body channels into this analysis. So what is a 3-body channel? If you imagine the interaction of a triton impinging on another triton, one of the very common 3-body final states for that is an alpha particle and 2 neutrons. So that would be a 3-body channel. Typically very difficult to take into account, but we've recently made some advances in that topic. And I should say, all of the work that I'm presenting on our matrix is done in collaboration with Jerry Hale at Los Alamos. So just to give you an overall impression of the compound systems that we study, I'm going to just list them and tell you a little bit about some of them, but I won't go into any detail, except in 2 case studies towards the end of my part of this hour-long session. So a compound system basically is either a stable or a metastable nucleus, and that's what's listed on the left-hand side. Channels are generally 2 or 3 body sets of particles that couple to a particular compound system. That's what's given over here. And then here I've shown the energy range of the data that we have and are analyzing with the R-matrix program, which I'll talk about more later. So for example, for A equals 4, one of the compound systems that we've analyzed is the helium-4 nucleus. And just counting up neutrons and protons, so this is, of course everybody knows, this is 2 neutrons and 2 protons. It couples to a proton and a triton, a neutron, a helium-3, and 2 deuterium. So one can imagine that the reactions or scatterings that go through the helium-4 compound system correspond to, for example, a proton impinging on a triton, and that going to a metastable state of a helium-4, and then that helium-4 dissociating back into a proton and a triton. That would be the elastic scattering channel. Or you could have the proton and triton go to helium-4, and then that decay to a neutron and a helium-3. So this is the sort of heuristic that we'll use to describe reactions, but let me emphasize that the R-matrix program does not require any interpretation about the metastable intermediate state. It's just a way of thinking about which channels couple to a particular compound system. And then you can play the same game with the helium-5. So this is very important reaction in astrophysical settings and other settings. Deuterium impinges on triton. It goes to a helium-5 nucleus, and then that falls apart into a neutron and an alpha. So that's, the neutron has 14.1 MeV, and the alpha takes up the rest of the energy with about 4 MeV. So this is a very important energy-producing reaction in astrophysical scenarios. And then these are, for higher A's, a list of all of the existing unitary parameterizations of data that we have. And many of these reactions are not incorporated, to my knowledge, in any of the existing BBN codes. So one of the research lines that we're pursuing is to put in the full set of unitary reaction amplitudes into the existing BBN codes. That's ongoing work, so I'm not going to present that today, but you should keep an eye out for it because it'll be out soon. Today I'll focus on one of the A equals 9 systems, a little later in the talk, 9 boron, and then also the reaction neutrons impinging on oxygen 16 going to an alpha and carbon 13. And we'll see in both of those cases how unitarity is important. Just to give you an idea of what these analyses look like in terms of the data and our fits to the data, I'm showing the neutron carbon-12 total cross-section, and you can see it's a very rich spectrum of resonances that are extremely narrow. So in order to get these plots, we have folded in things like experimental features of energy resolution, and we've broadened the peaks to account for energy resolution effects in the detectors. I just want you to get a sense that, doing these unitary parameterizations of data is a little tricky because you're kind of looking for the needle in the haystack that allows you to find where the resonances are and take into account the fact that these resonances, if you look here, there's a very classic signature of an interference effect between a very narrow resonance and this broader 1/2 minus resonance right next to it. You can see that that interference effect is driving down the cross-section. Now, you're not going to get that kind of effect correctly and the resonance spectrum right unless you're doing unitary. Of course, you can fit any curve to it, but your amplitude that you have underlying this R matrix analysis takes into account conservation probability and allows you to do very, very nice things like get these overlapping resonances correct. Here's neutrons on carbon-13, total cross-section. I should mention that this is a 2-channel analysis. Neutrons carbon-12, and then the other channel is NN prime, so inelastic neutron scattering. And then this is a single-channel analysis, neutrons at carbon-13. The reason that this is being done is because existing analyses do neutrons on natural carbon-12, which is a combination of these two. We wanted to split those out for some particular reason. Okay, so what is the nuclear reaction network? I keep referring to it, but really what is it? And how is it typically or conventionally done when you don't use a unitary parameterization of the data? Basically what folks do is they look at a single process. So let's take neutrons on carbon, let's take neutrons on oxygen-16 as an example. So if you wanted to parameterize the cross-section in that case, you would get the integrated cross-section, say, from the experimental group. For neutrons on oxygen-16 goes to alpha carbon-13. And then you would choose a fit form for it, and you would fit the a non-resonant and narrow resonant parameterization form through these data points. And then that would allow you to compute the Maxwell-Boltzmann averaged sigma V bar that both I and Carla spoke about yesterday. That gives you a reactivity, and then those are the coefficients that go into the nonlinear set of ordinary differential equations in the reaction network. The thing that's dangerous about this is that the cross-sections themselves can have large systematic effects. In particular, the normalization can be off, sometimes by 10%, but I've seen it up to a factor of 2. And the reason is because, if you think about what the cross-section is, it's a number rate into a particular angular detector, typically. And then what they need to know in order to give you a cross-section is they need to know the flux on target. And that's a very difficult thing to measure usually. I'm not saying that experimentalists haven't perfected an R form, but our experience is the normalization can have significant systematic errors beyond what's quoted. So the way around this is to do this multi-channel unitary analysis, and that's the remainder of the talk. Just to remind you, we saw it yesterday, so here's the Boltzmann equation reduced to the number density level. This is a toy model for a single reaction. There's sigma V bar, the coefficient of the reactivity, and then here are the number densities of the reactants. And you're taking the Maxwellian average of sigma V, which turns out to, the integrand is the energy times the energy-dependent integrated cross-section times the Gibbs factor, or Maxwell factor. So let me just say again that, sometimes unusual approaches are taken to getting the sigma V bars. Going from worst to best, often people will guess when there's no data or theory. And this is the idea behind Thales. So I don't mean to impugn Thales here because it's a necessary evil. But what they've done is they've said, we're going to give a cross-section for any reaction that you can think of so that you can run a code on it that solves this reaction network equation. So you should just be aware of what Thales is used for and what's behind it. Another thing that can be done is if you have the resonance spectrum of a particular compound system, you can parameterize that resonance data with a smooth form for the cross-section, and then you could turn that into a sigma V bar. That's also done. Fit to experimental data, so you have an integrated cross-section as I described in the previous slide, and you fit a smooth curve in energy through it, and then you turn that into a temperature-dependent sigma V bar, and then ultimately what we do. Okay, so let's go into a little bit about the scattering reaction formalism. How, in particular, is the transition matrix amplitude related to the data? So we start with the scattering matrix, which is a unitary matrix. And you'll probably remember that from your quantum class that we split this unitary operator into the unit matrix, which describes nothing happening, and the transition matrix corresponds to a scattering event. And so squares, the modulus square of this complex number is related to the observable of, to a variety of observables of the scattering particles. For example, here's the unpolarized differential cross-section. There's a kinematic factor. You average over initial states and sum over final states of the amplitude for the particular process to occur. That's the old quantum mechanics rule from Max Born. And then that will give you the angle-dependent differential cross-section. The polarization asymmetry, too, is expressed as a sum over bilinear products of the T matrix amplitudes, but I haven't written that out. But the point is that any observable can be derived from sums of products of bilinear factors of the T matrix element. And just to remind you, in case you haven't seen it in a while, the differential cross-section is related to the integrated cross-section by the integral overall angles, and then ultimately that will be thermally averaged to give you the sigma V bar, to give you a temperature dependent. So knowing this about the scattering matrix and the fact that it's unitary, what consequences does that have on the form of the transition matrix itself? The first line is the expression of unitarity. So I have some initial state. I've inserted between the scattering operators a complete set of states and summed on them. That's the sum over n. And then the final state is what you're going to observe in your detector. And that has to be won by conservation of probability. I've just rewritten the expression for the S matrix as 1 plus proportional to the T matrix. There's a density of states factor in here, which is just ensuring that, as in the old-fashioned, no, that's not right. Just ensuring that energy is conserved. And then if I insert this expression for S into the unitarity constraint on S, I get out a relationship between, on the left-hand side, terms linear in the T matrix amplitude. On the right-hand side, I get terms quadratic in the T matrix amplitude. So this ends up being a remarkably strong constraint and one that's fairly difficult to implement. You're probably familiar with one of the consequences of this relation in terms of the optical theorem. If I take the forward scattering matrix element on the left-hand side, so I equals F on the left-hand side and, of course, on the right-hand side, then I can write the left-hand side as the imaginary part of the forward scattering amplitude. F is just kinematically proportional to the diagonal matrix element of T. And the right-hand side, you can, when I equals F, you can write it as the total cross-section. So this is the good old optical theorem. But this constraint does not only imply the optical theorem. It also implies stronger constraints. For example, suppose someone gives you a full set of unitary of T matrix amplitudes that satisfy unitarity. So what I mean by that is you have a whole bunch of channels. So let's take the Helium-5 compound system, for example. That consists of scattering, so neutrons on Helium-4, elastic scattering, and then neutrons on alpha goes to DT, for example. Those would be the two channels. So T would be a 2x2 matrix in channel space. But suppose someone gave you all of these and they said, hey, they're unitary. You could check that. You put it in here and you make sure that's right. But now, say you wanted to do a test of some other thing and you arbitrarily scaled one of the matrix elements by a factor of 5. When you plug those matrix elements back into the unitarity constraint fails. So you can't scale the T matrix elements by any factor and expect to preserve unitarity without changing something else. And you can't also change the phases of these T matrix elements by any amount, or unitarity constraint fails. So this is a very important and tight constraint. And I'll show specific examples of how that happens. Now let's talk very quickly about the R matrix. What is it? Basically what you're going to do is you're defining two regions of configuration space, the interior and the exterior. The interior refers to inside the compound nucleus. So let's think of Helium-5 throughout the discussion. So that inside this region, which is a schematic of the interior region in the Helium-5 system, is when all 5 nucleons, the 3 neutrons and the 2 protons, are close to each other. And then these regions out here are the exterior regions, and that corresponds to when the Helium-5 compound system has been broken into 2-body clusters. We don't consider 3-body clusters. We don't consider arrangements of 5 nucleons into 3 clusters, is what I mean. We have ways of treating that, but that's a little bit more involved discussion. And so this channel might correspond to N-alpha, while this channel might correspond to DT. There's a third channel here that could be, I don't know, it could be an excited state of Helium-4, for example, and a neutron, although not necessary to think about it. So the canonical reference for how this is done is an absolutely unreadable paper by Lane and Thomas from 1958. Much better than that is a paper by Claude Bloch in the 60s. I'll just mention it in case you're interested in following up on it. That is a really good reference. So the channels are just separated pairs, as I described when talking about the figures, but they also correspond to different quantum numbers. Here's the spin basis total spin basis, total J basis. You can refer to the channels in any of these. Then the boundary between the interior and exterior regions is known as the channel surface. The channel surface is the union of all the possible channel, of the locus of points described by all of the channel radii, and we just collectively denote that by A sub alpha. The channel surfaces are rather complicated geometric objects that are fun to think about. So here's an example. Let's take the beryllium-8 compound system. For example, we have a proton impinging on the stable lithium-7 nucleus. That goes to a metastable state of a beryllium-8. And then that can decay into any of these possible channels, and for each channel you should think of a different exterior region. Is that clear? And so the R matrix formalism is basically, you ask, if I solve for the wave function inside the interior region, how do I join that to the known solutions, which are just the scattering wave functions in the exterior region? Another way of saying that is, if I determine the Green's function in the interior region in the presence of a particular boundary condition, how can I parameterize what's happening inside without exactly solving that equation? And this is a schematic of how we do that. So in the interior region, you have a Hamiltonian, but because you've limited space-time to be finite in extent, you can no longer use the typical argument to ensure hermiticity, which is when you go to large radii, your wave functions all fall off. So in order to maintain the hermiticity, you have to insert an operator that allows you to do that. It's called the Bloch operator. It ensures that the sum of the Hamiltonian and this Bloch operator is a compact Hermitian operator. Okay, does that make sense? So you're changing the boundary conditions that you usually use in quantum mechanics by introducing this Bloch operator. And this Bloch operator looks like this. So it's a thing that it's got a derivative and a set of constants. And this projection operator, which is basically, it turns out to be a Dirac delta function in position space. And so at a particular position, the channel radius, the boundary between the interior region and the exterior region, you're enforcing a particular derivative or even logarithmic derivative on the wave function. So this is a nifty way of solving a boundary value problem. Rather than explicitly state the value of the derivative at the surface, you insert an operator that does it for you, and then you just determine the Green's function corresponding to that operator. It's a nice little trick. And then if you take the transition matrix element in the channel space, so each of these C's is a particular channel wave function, scattering wave function in the exterior region, but its value at the channel surface, and of this inverse operator, which is the Green's function, so the propagator inside the interior region, then you get the R matrix. And you can show quite generally that this is a meromorphic function, real, very nice properties. And so you can parameterize it in terms of the products in the numerator, which are called reduced widths. So you're summing over a bunch of energy levels inside the interior region because you've discretized the system by putting this artificial boundary condition at the channel radius. So those are the energy levels, and these overlaps just give you the reduced widths. So basically the strength of the coupling for the scattering states to these interior energy levels. that's basically what I said all over here. So any questions about R matrix? It's a neat thing. So there are people who, we're going to parameterize this set of expansion parameters, let's call them, for a finite number of energy levels. Of course, because it's a discretized system, this in principle should be an infinite sum over energy levels, but we're going to use just a finite number of them. Okay, and this tells you a little bit about how the code works. We have the data, we adjust the energy levels and the reduced widths to describe the data via chi-squared minimization process. And so when you do that for a coupled channel set of data, so you have, let's say, integrated cross-section for the elastic channel and a reaction channel and maybe the total cross-section. This formalism allows you to parameterize that complete set, that multi-channel set of data simultaneously. So for example, here's the details of the oxygen-17 analysis. So the neutron oxygen-16 channel radius is assumed to be 4.3 Fermi. This is we do up to F waves, G waves. The alpha carbon-13 is slightly larger channel radius and up to H waves. You should keep in mind the fact that the channel radius is really just a regulator of the theory, and so it doesn't have a lot of meaning. This might be smaller than you anticipate, but in fact, what you can do is show via a renormalization group type analysis that if you tune the channel radius, that just means that it renormalizes your reduced width couplings and the energy levels. So it's not a physical parameter. It's just a regulator of the theory. So here are the energy ranges of the data. So this is the channel configuration. Here's the data that we're fitting, energy, number of data points, and data types. You can see that these data sets are substantial. And so we're getting very good constraints of the T matrix amplitudes. So what happened with this this particular compound system, the oxygen-17 compound system, is sort of an interesting story. Back in 73, Baer and Haas did a measurement of the alpha N reaction channel, and they came up with the black lines. Then in 2005 at Bochum, I believe it was Bochum, the Harrisopoulos group did another measurement of it. You can see that some of the structures are reproduced, but the normalization is significantly different, off by a factor of a third in some places. This is a later measurement by Heil and company. And what they've shown is that they're in agreement, although there's no direct overlap. So the circles are the 2008 measurement. The Harrisopoulos data is the triangles. There's not much direct overlap in the region here, but at least where they do overlap, you can see that maybe the Heil data, the 2008 data, is more consistent with the Baer and Haas data, which has these open triangles, but doesn't overlap. But you can kind of imagine continuing the red circles up through here. Anyway, the point is that you have conflicting experimental data. Who should you believe? And so unitarity can help you. Basically, what we did was applied the analysis I showed 2 slides ago and did this exercise. So we fit we fit the 1973 data, and we get a pretty good chi-squared for all of the data. I'm not sure I wrote it down here. But roughly, I think a chi-square per datum of 1.4, 1.5, something like that. And then that's without the 2005 data that perhaps is controversial, that has the lower normalization. Then we take out the Harrisopoulos data and replace it with this, we take out the 1973 data, we put in the 2005 data, and just try and fit that. Consistent with the other reaction channels, the total cross-section and the elastic data. And what you find is it's impossible to get a realistic fit of the data with a chi-square per datum less than 2. Unless you allow the normalization of this 2005 data to float. So in your fitting procedure, you just scale the complete data set by an energy independent constant. And then what you find is you basically get back to the 1973 data. So because of this impossibility of adjusting the normalization according to unitarity constraint, the fit is telling you that if you do a multi-channel description of the data, the normalization is pretty tightly constrained by the other data. So if you want to call this theory input, that's fine. To me, it's just conservation of probability. Okay, and this actually has an effect for BBN. I'm running out of time because Evan is going to talk about the observational issues. But I just wanted to tell you that there's a publication about a specific system, the boron-9 system. Seibert and Pospelov back in 2009 postulated that there might be resonant enhancement. And basically we were able to show that that argument was flawed on the basis of a unitary analysis of the boron-9 compound system. And these are the details about that analysis. If you're interested, we can certainly discuss it offline. I'm not doing that. This is the data that was fit to it. You can see that our description is fairly good. There's room for improvement in parts of it. But like I said, basically what it shows is that, first of all, the resonance spectrum that's in the nuclear data group tables from the Triangle University Nuclear Labs Tunnel Nuclear Data Group turns out not to be well supported by this. So the lesson there, the take home is be careful looking up resonance parameters for the nuclear data group. Ask, is this a unitary parameterization of the data? I'm not sure. And then the second thing is, if you look at the strong resonance signals, we can characterize whether a resonance is strong or weak through our analysis and whether or not they're important, potentially for astrophysical processes. If you look through the list of strong ones, there's nothing that would succeed to the description that Seibert and Pospelov required for the 9-boron compound system. So resonant enhancement of lithium destruction, which is needed in the models. Remember, lithium-7 is over-predicted compared to the observed lithium-7 primordial component. So what you want to do is find reactions that kill lithium-7 production or beryllium-7 production. And they were looking for a resonance to do that. We were able to say, even though there's no data down there, we were able to exclude that possibility on the basis of unitary parameterization. Okay, so I gave you a little bit of sense of what we do at the lab in the light nuclear reaction program, and I went really quickly through how the R matrix parameterizations enforce unitary. I hope that's the take-home message that you remember. So now Evan's going to talk about how these.
Are there any questions for Mark?
Yeah. So you've mentioned examples of like pretty light nuclei that are not very drafty. Is it also feasible to do this unitary analysis on very heavy nuclides?
So very heavy, I would say no. And that's because the proliferation of channels that opens up very quickly, it just kills you in terms of the size of the reaction matrix that the transition matrix that you would have to consider. But, you know, you may have noticed that by light nuclei, I mean compound systems with number of neutrons and protons up to 20. So, okay, not,
For our process, that's still
no,
light.
no, you can't do it for our process. But there are effective descriptions, for example, statistical descriptions, statistical Hauser-Feshbach, things like that, and I'm talking with colleagues in our group about ways of partially implementing unitarity for those methods.
Do you have any sense on, so I'm using the React data for our process calculation.
Right.
Do you have any sense as to the quality of that? Like, is React like pretty good, or do you know that it has like serious flaws?
No, I don't know that for a fact, but I can tell you that you know, you can ask, you know, questions about, in particular, normalizations used to determine cross sections, and ranges of energies that were studied, number of channels that were. I mean, the more channels that are open, the more suspect simple curve fitting is going to be, right? I mean, I think that's the lesson that you get from the low number of nuclei, low number of nucleon sector.
I got a question for you.
Yes.
So Evan's about to show you that, of course, one of the things we can measure in astronomy extremely accurately, amazingly accurately, is the primordial abundance of deuterium. To the point where eventually it's going to be uncertainties in NP gamma to deuterium, right, that are limiting, will limit our ability to get the primordial abundance. So what are the prospects for doing really high precision ab initio calculations on that reaction channel to get the cross section?
So you're talking about NP capture to deuterium.
Right.
So the prospects are very good. In fact, the prospects have already been realized. So there are people who do effective field theory calculations using chiral power counting schemes that have exactly done that, that reaction. The only limitation of those is that you can't get very high in energy. So if you're looking for tens of keV or 100 keV.
Yeah, we're going to do this, of course, in BBN, so the temperature is going to be 100 keV, meaning the average energy is going to be 300 keV.
Right. So
how do we get it in that regime?
yeah.
Is there any experimental way to get at this, or it involves neutrons? Probably not. Huh?
Yeah, I mean, data is definitely an issue if you want to do unitary parameterization for the nucleon-nucleon system. That's simply a fact. I thought you were going to ask me about proton capture on deuterium, but anyway.
No, I just want D itself.
Yes,
So
yeah.
the astronomers are telling me that the limit now will be that uncertainty in, NP gamma.
Yeah, I think that's true. So the prospects are to go to higher orders in the chiral effective expansion. Very difficult. I don't think anyone's rushing to do that. And then the other issue is if you can give me more data, I can use a phenomenological approach to ensure that it's well constrained. But I would still say that at the cross-section level, you're looking at 10% uncertainty as being pretty good. So, not that great.
Next one.
Thank you. This one.
Needs to go on first.
Which one goes on top? Look, it's tough to read.
All right, everybody can hear me through the microphones? I think so. So, if you don't know me, my name's Evan Groves. I'm a graduate student here at UCSD, working in the Fuller Group. So this is not my area of research. We do not do astronomy. Please, realize that. So what the idea was is just to present some information on actually what these astronomical observations are, so that when we do the workshop this afternoon, you kind of know where these numbers are coming from. All right, so please just, I'm not an expert in this, so if there's anybody, if I say something wrong and people realize that, please raise your hand and correct me, since it's supposed to be an educational experience. So let's just dive in. All right, so what you're looking at here, this is a result from Izatov and Thwan. They are looking at how the primordial abundance, the primordial mass fraction of helium depends on some metallicity parameter in low metallicity H2 regions, which are primarily in compact blue galaxies. So you have roughly 90-something data points in this sample, right? This metallicity parameter that they're using is the oxygen abundance, but you don't have to use oxygen. You can use something else if your experiment dictates. And so basically the idea is that you have all these points, all right, these low metallicity points. This is 10 to the 6th times the oxygen abundance. And you make a regression line through this data. And you draw that line all the way down to 0 metallicity, and that's primordial helium. So you get excellent statistics because you use a lot of data points, and then you kind of just estimate a systematic uncertainty, at least in this analysis. I'm sure they do it more complicated than that, but I'm not exactly sure on what the details are. So this was 2010. In 2012, Aver-Olive-Skillman took the Izatov and Thwan 2010 data and just culled 15 regions from it, which they thought would be very representative of this trend. And so you can see their data plotted here. Once again, it's oxygen versus the primordial helium abundance. The 0 isn't set on the axis, so there's 0. So there's their estimate for the primordial helium. They have a little bit larger error than Izatov and Thwan, lower amount of data. Then last year, Aver, Olive, Porter, and Skillman added a few more data points to this and somehow got a larger error. So I'm not exactly sure how the variance changed from these two papers, but it somehow did. So again, right, this isn't any new data. All right, you have to. It's very difficult to do this measurement. There's multiple systematics. None of these are measured. These are all modeled. And so in order for Aver, Olive, Skillman, Porter, they had to do a Monte Carlo Markov chain analysis in order to look at these different effects. I'm not at all well versed on how these effects change the primordial helium abundance. This one that's underlined is just thought to be the biggest contribution to these systematics. So this list of systematics is from the Izatov and Thwan paper, so it's certainly not exhaustive. So another way to find the primordial helium abundance is to look at how diffusion damping changes in the CMB. So Planck has multiple measurements for the primordial helium mass fraction, I should say. These are all 2 sigma results on the error bars. The Planck is just the Planck data set. WP is WMAP, polarization data. Planck should be coming out with polarization data in a few months, I believe. High L is high L data up to a L of about 9,500 from Atacama Cosmology Telescope, so in Chile, right? And so that helps with your calibration. So that's for this first data set. The second data set, this is baryon acoustic oscillations for BAO. I'm not sure what data set that's from. It's probably BOSS if it's from, if Planck was using it in their analysis. And then this last data set is Hubble Space Telescope. And so when you see, you maybe have heard about some tension between HST results and CMB results, and so you can actually see that by a lower primordial helium mass fraction. And so this is due, right, because Hubble prefers a larger value of the Hubble parameter as compared to the CMB results. But if you look, these are 2 sigma errors, so these are almost all consistent with one another at 2 sigma. But most importantly, that this result for YP assumes a standard N effective value. So we haven't really talked much about N effective and how it relates to diffusion damping, but it suffices to say that all these results are done with a fixed N effective. Okay, so they're not necessarily, this is not necessarily being done self-consistently. Okay, moving on, deuterium is also measured from in primordial systems. So this is a plot showing the flux in CGS units as compared to a velocity parameter from which you can get a, this is a velocity with respect to a certain redshift of this damped Lyman alpha system that they're looking at. And so this is from Tytler's group here at UCSD. You can see, right, this broad, I don't know how well you can see it on the screen, but you can see this, if you can see this broad absorption spectrum for the hydrogen. And if you look at these higher excitations, you start to see this deuterium absorption spectrum. And so there's only 5 of these systems, at least in 2003, that Tytler used. And so his error, right, is on the order of, this is a 1 sigma error, so it's on the order of 20%. For deuterium. If we go to a little bit more modern result, this is from the Cook group done with Max Bettini, I believe, at Cambridge. This again is 5 systems. It's not the same 5 systems as the Tytler result. This red, or this orangish reddish data point is there is a new quasar system that they found. What they're plotting here is the log of the deuterium abundance on both axes versus, in this case, like a metallicity parameter for oxygen, and in this case, a column density for hydrogen. And so this green stripe here, right, is done with using a BBN code, right? So this is a prediction from BBN, all right, versus the data points that they found. And so with this such a small scatter, correct, right? So you can see right here, like this is 0.022068, right, which is the Planck baryon number determination. And so from here, they get excellent statistics. This is not only a statistical error, this is also a systematic error for their estimates. If this is to be believed, like George kind of intimated earlier, this is an excellent value. And so this is basically the latest and greatest there's only 5 of these systems that Cook picked. With the advent of 30-meter class telescopes, there could be very, very likely there will be the discovery of more of these clean systems. And so there are systematic errors in looking at this deuterium abundance, relative abundance. And so this instrumental broadening and this quasar continuum at 0 level, they think they can eliminate very well. This cloud model is more difficult, but both the Tytler group and the Cook-Bettini group are very careful, from what I can read, in their selection of systems. Hence why you only see like 5 different systems in these data sets. So this is not this is the main source of systematic error, but they think they do a good job of maintaining a low error budget. So there is a measurement for primordial helium-3, and by is a measurement, there is one measurement. All right, so they do not look at any sort of large redshift abundance of helium-3. So this is galactic helium-3 that Bania, Root, and Balzer have done, the latest being in 2002. For whatever reason, it's just not I don't know what the word is, trendy, I guess is probably the right word to use, measurement. And so they're looking at this in the ISM. So obviously there is stellar and cosmic ray processes that can create helium-3, but the model estimates give it as a very low amount compared to this number. So this number is an upper bound, but it's thought to be a good upper bound. All right, is this gonna, okay, it's going away, thank goodness. All right, now into moving on to conclude, the last abundance that's relevant is the lithium abundance. So this is a plot from the seminal paper by Speet and Speet in the early 80s. And so here what you have plotted is temperature decreasing from left to right versus the abundance of lithium. And so these the Speet and Speet they looked at 5 new stars, but there's also there's also some other data points on here from a different data set. And so these are these old population 2 halo stars, which are thought to have formed from, I don't know if pristine matter is the right word, but basically from primordial matter. And so what you're seeing here, right, is that if you decrease the temperature, you get these larger convective zones within the star. And so you start to destroy the fragile lithium. However, if you go up to a high enough temperature, the convective zones actually get shallower. They don't go deep enough into the star to actually burn up, and so you see this flat plateau here. And so I haven't read this paper carefully. This is the estimate that they got. So the idea being that this flat plateau is the primordial abundance, since it isn't changing with temperature. And so this error, I think, is only statistical. I don't think there's any systematics in that error budget. More recent analysis in 2000 by the Ryan group, they looked at using a galactic chemical evolution model. And so here they have the lithium abundance, relative abundance plotted against the metallicity in terms of iron with respect to the sun. And so you still see, at low metallicity, you still see this Speet plateau. These data points over here at higher metallicity involve other processes such as cosmic ray spallation. According to the Ryan group, their claim is actually similar to the deuterium group's claims that now this air is actually constrained better than what the nuclear reaction data gives. This error is larger than what we had for the Speet value because this does include some sort of systematics. The latest value that I could find was from 2010 from the Spordone group. And again, they have a larger, this value for the lithium abundance keeps on increasing, but it's still considerably lower than like 4 times 10 to the minus 10. So there's a plethora of systematics for lithium. And there's no way this list is exhaustive. I'm sure there's other things that, I don't know who said it, but there's unknown unknowns on this list, no doubt. So the idea, right, for this first one, IMF, the initial mass function of the population 3 stars, that's not real well known, and how those stars would mix with the interstellar medium. Diffusion, gravity waves, and rotational mixing within these stars, if possibly the lithium is being destroyed within the stars. Turbulence is another complicated issue within the stars. There's also an issue with maybe the Speet plateau isn't really a plateau, that perhaps it changes with low metallicity. And so when people look at that, they also have to look at the binary systems and include these models of non-local thermodynamic equilibrium in the stars' atmospheres. So this is a complicated problem, to say the least. So the punchline is that we have on this plot, was done by Nao Suzuki in the Tytler group here at UCSD in 2006. We have plotted, I call this baryon number, but this omega BH squared, or if you want, you can convert that into baryon to photon ratio. And then on the vertical axes, we have either mass fraction for helium-4 or relative abundance for deuterium, helium-3, and lithium-7. This pink stripe is the WMAP value, but the Planck value is basically right on top of this. It hasn't changed. So you can think of this as also as being indicative of current CMB measurements. And so helium-4, right, this is an Isotov and Thwan from early 2000s, I think, value. This deuterium measurement is from the 2003 Tytler value. This helium-3, you can see there's an arrow, so this is just an upper bound from the Bania-Ruud and Balzer. And then this lithium-7 is from the Ryan group, the plot I showed with the changing lithium and metallicity. So this is obviously the triumph of standard BBN, okay? The fact that this deuterium observation is spot on with the CMB. Helium-3 is certainly consistent. Keep in mind, right, these boxes look about the same size, but if you look at the relative scale, right, this is actually a very small box. And so that does agree with the CMB, but there's notable systematics and estimations of the error on that. So don't exactly, take this with a grain of salt, so to speak. But obviously the problem here, right, you can see is that the lithium does not agree. It predicts a much lower baryon density if you were to use this as a to try and make this consistent with standard BBN calculations. And so it's off by about a factor of 4. This is about 1 times 10 to the minus 10, and what you're going to see for the predicted abundance is it's about 4. So I should say, right, since this plot, the Tytler group basically just added in these little boxes. These curves, I don't know if you can tell, but there's a thickness to the curves, and so that represents a Monte Carlo modeling of the nuclear reaction errors. And so you can see for this lithium, it's actually it's thicker, right, than for, like, say, helium-3. So these curves, the Monte Carlo modeling is actually Nolet and Burles, and the curves themselves are Nolet, Burles, and Mike Turner from a paper in, I believe, 2001. So the takeaway message here, right, is that lithium, there seems to be a problem there. And so what we'll do, just to conclude, what we'll do in the workshop is we already have a BBN code which will calculate the abundances with respect to a certain baryon number, and so you will parallelize that code so that you can actually generate the data for this plot. Not the thickness of the lines, we'll just generate single lines. But from that, you'll be able to make this plot for your own research, but we'll use updated values. Okay, specifically, right, the Cook value for the deuterium. So unless there are any questions, I will stop there. Okay, great. Let's have a break or something.